All right. Welcome everyone. It's so awesome to see so many of you here. My name's Hugo McDermott-O'Peskin, and I'm the MDAnalysis side lead and for the streaming project that we're running with ASU. And yeah, I was super excited to show you all the work that we've been doing in this space in collaboration with ASU, kind of looking at streaming and inline trajectory analysis with MDAnalysis. So welcome again. This work's been a fantastic collaboration between MDAnalysis and the Hayden and Bechstein labs at ASU. They've done most of the heavy lifting, and it's our pleasure to have them here today as superstar guest speakers to tell us all about the stuff that they've been doing. A big thank you also to the National Science Foundation, who have funded all of this work through a CSSI grant. It's been obviously essential to driving some of this work. Thank you also to NumFocus, who sponsor, we're a fiscally sponsored project of NumFocus, and they do a lot of the administration for MDAnalysis, providing us the support, a lot of the support we need. So thank you a lot to them. I'm just going to run you quickly through our agenda. So first, we're currently in the welcome that you can probably see on the screen. I'm then going to run you through a little bit of background about MDAnalysis and the MDAnalysis ecosystem. Then Matthias will take us through a big picture view of streaming, followed by a Q&A session. Then we're going to have Amru take us through some MD packages, how to work with the IMD client, and a demo. We're then going to have a break where you can get some water, relax, hopefully shake out your limbs. And then we'll come back and we'll have an interactive activity with Lawson about writing your own stream analysis. That'll be really fun. And then some more technical developer details about streaming functionality within MDAnalysis, followed by a Q&A session as well. Once we come back from the Q&A, we'll have Hee-Kun take us through some applications, looking at velocity correlation functions and things like ion channel permeation, some really cool scientific things you can do with streaming, followed by another Q&A. And then Matthias will take us through some future directions. After that, we'll have a 20-minute open forum for you to ask any questions that you'd like to ask, and then we'll have some quick closing remarks. So because there's this open forum at the end, if you don't manage to get your question asked in the in any of the Q&As, you can either save it for the end if you'd like to ask out loud, or please just throw it in the chat. Okay, so just a few bits of admin. This meeting will be recorded, as I said before. There's already a fantastic number of us here, very exciting. But there's probably too many of us to just all unmute ourselves at the same time and start talking over each other. So when we do the Q&A and the open mic sessions, could you please raise your hand if you'd like to talk, and then a member of the team will call on you verbally, and then you can unmute yourself and you then ask your question. Hopefully that'll all go smoothly. It's important to note that this event is administered under the MDAnalysis Code of Conduct. If you've never seen the MDAnalysis Code of Conduct, I really suggest you check out this page. I'm not going to run through it all with you now, but it basically boils down to be kind, respectful, and as I see it, be a good person. So if you haven't come across that before, I'd recommend checking that out. Just important to note that you should be treated with respect in this space. Also, if you're having trouble with any of the interactive components, there's quite a few interactive components. Please just ask in the chat. Hopefully a member of the team will be able to help you. We also have a little cheat sheet that we'll set for some of the issues that you might encounter. Hopefully none, but we'll send that around at the time. And the workshop material will be made available free of charge under the MDAnalysis org, as always. But just note that currently this, due to some technical issues with the way we're running the demonstrations and some of the billing, this currently redirects to a fork of a semi-fork of this repository. But this will be the final resting place of the workshop material once the workshop concludes. All right, that concludes our our little intro. You're stuck with me for a little bit longer, though. I'm going to give you a little overview of the MDAnalysis project, who we are, what we do, and maybe a little bit of history. So, full credit to Oliver Beckstein and Jenna Swatut Goddard, who's our wonderful MDAnalysis community manager, who originally prepared these slides. I stole these slides off them, so thanks to them for preparing them. All right, I would say at its core, the MDAnalysis community is really just all about working with molecular simulation data, and making working with molecular simulation data fun, enjoyable, easy, and scientifically impactful for our users. At the core of that is the Python library built for analysis of molecular simulation data, and it's written by scientists for scientists, which I think is a key reason why it's been rather successful over the years. So, especially early on and continuing today, the majority of the development has been open source and community led. So only recently have we managed to get some money to work on MDAnalysis. The majority's been non-funded work, and so it's really been a community-driven effort. You'll hear that word a lot, community. So our full mission statement's on the left. I won't take you through all of that, but I do really think it boils down to being all about data for computational molecular sciences. I would also argue that MDAnalysis started around 2006, 2008. We're now a relatively mature, well-established library, and we're kind of have the opportunity to build for the longer term and focus on things like user experience, which is great. So it's a privilege. Okay, so a super brief history of the MDAnalysis project. It was started by Naveen in 2006 when he was at Johns Hopkins University, with two co-creators or early adopters being Elizabeth and Oliver. I'm sure many of you know Oliver. And it's been an open source project since January 2008, originally hosted on Google Code. We managed to get non-focused fiscal sponsorship in Jan 2020, which has been instrumental to help us grow and kind of scale beyond a core group of really dedicated volunteers. So again, it's very community-driven experience, as a lot of people, myself included, first became volunteers and developers, and then core developers and project leadership over the years. This is pretty standard for open source, but just to reinforce that, if you get involved and you put in the effort, you can really make something out of some open source contributions. And today we have over 200 contributors, and I would say many times more users than that. And it's one of the we're among kind of the top popular libraries for analysis of molecular dynamic simulations, as you can kind of see on the chart on the left. And you can also see just that this area, the analysis of molecular dynamic simulations and computational molecular sciences data in high-level languages such as Python is growing quite rapidly, if you look at the citation counts on the left. So maybe a quick mind map of some of the more disparate parts of the MDAnalysis ecosystem. So we obviously have the MDAnalysis core library, which I would say everything else is built upon, which is open source on GitHub. I'm sure many of you have probably been there before. We also have other software like auxiliary helper software, or maybe some more kind of interesting projects that we've developed that are also hosted under the GitHub MDAnalysis organization. Some of those are dependencies, some of those are experiments, but you can go and check those out. And a lot of these are focused around things like interoperability, such as converters with other libraries, or performance, or file type reading, or things like that. We've also tried to build out an ecosystem whereby people who are interested in more bespoke scientific applications of MDAnalysis can have their own easy to maintain package. So the best analog of this is the scikit ecosystem. So scikit ecosystem spawned out of SciPy, and one you might be familiar with, because SciPy couldn't contain all of the world's scientific code effectively. So the one you might be familiar with is scikit-learn. So scikit-learn is a so-called package of SciPy. Maybe it doesn't come across that way these days, but at least that was how the idea was started. And if you're interested to learn more about MDA kits, you can click on the link down there. I'd really recommend you do. It's like a vibrant and growing community of kind of more specialized packages that are built on MDAnalysis. We also do a lot of education and outreach. So that's why you're here today. It's stuck with me. But we run a lot of workshops. We also do quite a bit of mentorship. So we do Google Summer of Code, which many of you may have come across. We've also done, in the past, we've done things like Outreachy and Station 1 mentorship, which has been both instrumental to grow our community and also to mentor people who are just kind of getting started in the field. And also, again, that's the C word again, MDAnalysis is a community. So there's a lot of community forums that we connect on. I'd say probably the most active is Discord or GitHub discussions, but you can also find us on X, Blue Sky, or LinkedIn. And there'll be links to all of those later on. Okay, so what's kind of the key value add or workflow that people use MDAnalysis for? And I'd argue that it's pretty much this. It's you take a simulation trajectory produced with your favorite extremely powerful simulation engine, and you can kind of coerce all of that data into a common, easy to work with format. So we can read over 40 file types, and we can turn all of these into accessible and structured data, namely the NumPy ND array, which I'm sure many of you would be familiar with. You can then use pre-implemented analysis algorithms that we package along with MDAnalysis, or write your own to process your data to generate the scientific insights that you're interested in. And basically, because this is one analysis script for many different file formats, and I would argue Python's pretty easy to read, this is quite reproducible and could hopefully go alongside your manuscript, enabling other people to reproduce exactly what you've done. So this is the core value add of MDAnalysis, at least in my opinion, and hopefully why you're all here, or a reason, part of why you're all here. So an example of this might be if you wanted to do some machine learning on a molecular dynamics trajectory. So you would use MDAnalysis to extract features like times, positions, velocities. Maybe you want to compute more complicated features on top of that, and then you could feed it into your favorite ML package. So here's a great example of that from the wonderful Matteo Giacomi, who did some basically training a classifier on a trajectory of the MERD protein, which basically classifies its structures into open or closed from a simulation. So I guess the Python code is not so important, but basically you can get to a scientific result in probably under 100 lines of code with MDAnalysis, combining MDAnalysis and scikit-learn, which I think is really cool. Really cool and really valuable for the field. Another example of some of the things you can do with MDAnalysis. So the wonderful Brady Johnson has created this fantastic package called Molecular Nodes, which renders molecular data into these beautiful, beautiful images in Blender. I highly, highly recommend you give it a try. It can create, so there are just some example renders here, can make some very, very beautiful dynamic renders of proteins in motion. And that uses MDAnalysis as its file reading and analysis backend. So you can use MDAnalysis in a pure API based way to build your own programs as well. So we recently released MDAnalysis 2.8.0, continuing our MDAnalysis 2 series. But kind of where are we headed? So there's kind of two main branches. One is, as we call it, extending reach and detail. So Number one of those is streaming support. I'm not going to say too much more about that because I think that's you'll be hearing plenty about that today. And the other is what we call more scientifically aware operations. So better things like better interoperability with RD kit, using improved guesses to be able to kind of get more chemical or scientific context within your simulations, within the analysis of your simulation, sorry. And the other is always continuing to improve the user experience. So we're working on some parallelization schemes. That's been going quite well. We're also trying to redesign our precision model so that you can have better control over what precision things are being analyzed in. And we're also trying to Cythonize or C++ify those unreal words, but I think you get what I mean. Some of the slower critical code in MDAnalysis to make it more performant. We're also trying to improve interoperability, and we're always looking to support new file formats. Especially with plugins. So if you have your favorite file format and it's not in MDAnalysis, get in touch or open a PR. Alrighty, so here are some of our social links. This will pop up a few times this slide, so don't panic if you're desperate to join and you don't get to copy all of these down. But these are just some of the places that you can reach us and get in touch. Finally, some acknowledgements. So these are all of our. This is probably a few months out of date, but these are our 205 contributors. Without these people, MDAnalysis obviously wouldn't exist. It truly is a community effort, and all of the every single one of these people has added something new and unique to MDAnalysis, and for that we're really, really grateful. All right, so I think I'm going to pass now to Matthias to give us a first look into streaming.
All right, thank you very much. Let me share my screen so everything works. You can all see what I see. Yeah, thank you, Hugo, for the introduction into kind of the MDAnalysis world. Thank you all for joining. It's great to see so many participants and so many kind of familiar names and faces as well. So welcome to you all. I'm going to talk about basically the product of a recent project in mine and Oliver's group. And you can see here the contributors on our side, on Arizona State University, as well as on the MDAnalysis side, where we basically implemented a streaming interface for MDAnalysis. So first important question is, of course, why would you want to do such a thing? Why would you want to stream MD trajectories in the first place? Most obviously, of course, you can analyze your trajectories on the fly. You have a running simulation either on your computer or on some remote server. And while the data is being generated, you can already access it and you can analyze it. So a few things that allows you to do is you can analyze, for example, fast sub-picosecond processes without having to write out really, really large directory files that basically contain all this very high time resolution data. That gives you easy access to things like solvent dynamics, hydrogen bond dynamics, hydrogen bonds breaking and forming in water, for example, diffusion, molecular vibrations. You can analyze friction using so-called force time correlation functions, which you will see in a second that this is otherwise, I mean, technically easy to do, but it gets hard when your simulations run longer and longer and longer for like microsecond timescales. You can also use that to detect events in your simulation. You can monitor arbitrary collective variables. Basically, you can write up any kind of analysis script in MDAnalysis. You use the stream data and you basically follow these collective variables during a simulation and detect certain events. That can be useful, for example, when you want to use weighted ensemble methods. They basically want to see if your simulation or one of your many simulations in many cases have reached certain kind of track points. Another thing that you can use this for is to monitor water ion flux, and you will see an example in this workshop as well. But this allows you to basically track the positions of ions, for example, when they go through a pore in a membrane with high time resolution so they don't miss any kind of events or don't have unambiguous things where the ions may move through periodic spaces instead of going through the membrane. Here you basically can see them at high time resolution without having to store the data at high time resolution. And last but not least, you can basically use it to control your output. Many MD analysis packages basically force you to store all the data for your entire system. There's nothing wrong with that. But because of disk space issues, you often can do that only at kind of larger time intervals. But now you have control over the stream of your entire data, and you can do whatever you want with it. For example, just filter out the protein coordinates, even post-process them, align it to reference structure, do kind of unwrapping, and store that as a separate directory with high time resolution that you can analyze later. So all of these things streaming allows you to do directly. Now, this fast sub-picosecond process, something that my group is quite interested in. So I will go into a little bit more detail on why this currently can be a problem and how basically streaming can solve this. When we talk about molecular dynamics simulations, when we advertise it to others or even ourselves, one of the selling points is that we can, especially nowadays, cover timescales over 9 orders of magnitude, which is pretty impressive. We can go from femtoseconds to microseconds or even multiple tens of microseconds, which is pretty cool. And you can see here from this graph what kind of different processes, it's a little bit biofocused here, but it's true for other systems as well. You can look what kind of processes you can see. You can look at vibrations, you can look at, as I mentioned before, solvent dynamics, hydrogen bonds breaking and forming, things diffusing around. You can look at more collective relaxations, for example, of dipoles. You see side chain fluctuations in proteins, proteins tumbling around, conformational transitions in proteins, and so on, so on, so on. But when we say that, we are also kind of lying a little bit, because when we run a typical simulation, can we actually use this entire data? Assuming kind of a run-of-the-mill simulation size of about 1 in 1,000 atoms, this is basically a bigger protein in water, or maybe a membrane protein, and you run a trajectory of just 1 microsecond, so 1 million picoseconds, and you want to basically access all these different processes. That means you have to store the data in your trajectory every 0.1 picoseconds or 100 femtoseconds to basically see what is going on here on this left end of that scale. If you do that, and even if you just store the coordinates of the atoms in your system, that means 3 numbers, x, y, z, for every atom. Every number is a single position floating point number with 4 bytes, gives you 12 bytes per atom. 1 in 1,000 atoms, 1 million picoseconds, and 0.1 picosecond time resolution. That gives you a file size of 11 petabytes at the end. So that is a problem, actually quite a substantial problem. What you and probably most of us are doing as well, this is unfeasible. So what you typically do is you reduce the time resolution of your trajectories. Instead of storing everything every 0.1 picoseconds, you often go to tens or even hundreds of picoseconds of time resolution. And that means essentially that you throw 99.9% of your data kind of away. It's generated during a simulation, but you have no real way of monitoring it. And that means this entire left side of this kind of dynamic range that I showed over here basically becomes invisible to you at this point. Of course, you can run shorter simulations that generate this data and at higher time resolution, but so you don't go to the microseconds time scale, but you may not actually reproduce exactly what happened in your longer trajectories, because when you run things on GPUs nowadays, things are not perfectly reproducible. So this is kind of a problem. And there's a lot of stuff that you miss. So this is a little bit of a specialty of my group and something that we often focus on: solvent dynamics in the environment of biomolecules like proteins. All these things happen on the picosecond and sub-picosecond timescale. So as I said, if you are not able to store this information, you basically just lose all of that. What we can usually do is we can track the, for example, dynamics of hydrogen bond networks in the environment of a protein. We can track the diffusion, we can track the vibrations of these molecules. We're particularly interested in vibrations of molecules against each other in the hydrogen bond network. And we have some techniques based on a method that's called two-phase thermodynamics that you will hear a little bit later about as well, that allows us to even extract thermodynamic information, something like the entropy of water molecules around the protein. And what we do is not just calculating these things as just bare numbers, but we usually resolve them in 3D on grids around biomolecules, so that you in the end get a grid with typically 1 angstrom resolution that gives you all these properties, which is nice. But in order to do that, you need high time resolution. If you cannot store that data, you have a problem. And that's exactly what streaming does for you. It gives you that data while it's being generated, so you do the analysis on the fly in parallel to the simulation. You're not having you're not required to store it permanently or even semi-permanently. You don't have to generate these large files. You just do the analysis while the data is coming in. You read the stream, process everything in the stream, and store your trajectory in whatever way you usually do it. That makes it feasible to actually store it longer term. But you do analyze all these processes on the fly. Now, before I go into the weeds of how we actually do this, I have to introduce a little bit of nomenclature. What we're using specifically is a TCP/IP socket interface to do this kind of communication between what we call a server in this kind of framework. The server is the MD simulation software, so your MD engine, which effectively serves the trajectory that it generates. Internally, we also sometimes call it a producer. What you will need from the server is you will need basically its address. You need to know which kind of node or which computer remote server is actually running this particular process. And on the other hand, you have a so-called client. In this case, that will be your MDAnalysis script or a Jupyter notebook or something like that, that receives the data from the server. We also internally sometimes call that consumer. In order to make that work, you need to specify a port number, a TCP/IP port number, basically to set a communication channel between the server and the client. And obviously, they need to be set to the same value for both of them. When you set this port number, there are a few things that you should take into account. This is used by many, many other processes as well that have to communicate with each other. So many of these ports are already used by other processes. Ports 0 to 1023 are so-called well-known ports, which you may not even be able to use without super user privileges. So basically stay away from those. Higher numbered ports are so-called register ports that you are usually free to use, but you may run into conflicts with other processes that are using them. That is usually not an issue. You basically get a warning message at the very beginning that this port is already used, choose a different one, so that is not an issue. If you go to even higher numbered ports, that's called dynamic, private, or ephemeral ports, they are free to use, and you should not really have problems with conflicts. But as I said, if you see a conflict that is not a big issue, just choose a different port. And in some cases, that is even done automatically for you. So in order to implement this kind of streaming interface, we don't have to start from scratch, which is great. We always, with many things that we do, stand on the shoulders of giants. And in this case, it's important to point out John Stone and his interactive molecular dynamics framework, but he already introduced more than 20 years ago, basically, at least initially, as an interface between the MD code NAMD and VMD, which many of you know for visualizing molecular dynamics directories, doing analysis of it, and so on. But this particular interface allows you to visualize your simulation on the fly and then interact with it as well, like using a haptic device or even something as simple as your mouse. In MDAnalysis, in VMD, you can basically grab molecules or atoms and pull them around. By pulling them around, you basically apply a force which is being communicated back to the MD engine and it's integrated into your MD simulation. You can do lots of cool stuff with it. One example is here by Mark Barton's group from 2022. This is really, really cool. And technically, it gives us a lot of the features that we already need. Not quite everything. This is why we have to do something, but it's a great place to start. This is what this initial interface looks like for IMD version 2. This is the original kind of implementation. Why it's called version 2, we're actually not aware of that, but it's just to avoid confusion. So this is the original. What it does is communicate coordinates, optionally also energies. There's some echo, okay, should be solved now. So it communicates coordinates, optionally also energies from your MD simulations, from your server side to VMD, which is your client. So you can see that over here. That is being sent from MD through this kind of socket interface to VMD, which is your client. VMD receives these coordinates and potentially energies. When you do something with it, you apply forces by your haptic device or your mouse, and that force is being communicated back to your MD and is implemented in the MD algorithm. So that's pretty cool. Why do we need to do anything? So why don't we just use that as is? Why do we need basically version 3 of this interface? What IMD version 2 does, it only communicates atom coordinates, which is sufficient for visualization. You can also modulate kind of a transmission frequency, basically only communicate data every 10 MD steps or whatever you want. So this is all great. But we need a little bit more. If we want to be able to do a proper analysis of these MD trajectories, what we need at least, and at least as an option, is, for example, something as trivial as the box dimensions. If you run a constant volume simulation, that's maybe not be a problem because that doesn't change, so you may know that beforehand. But if you run anything at constant pressure, that changes all the time, and you cannot properly compute distances in periodic space if you don't have that. So this is something that needs to be computed or communicated more specifically. In addition, for many of the things that I showed you, especially in water dynamics, we want to look at time correlation functions, molecular vibrations. For that, we often need atomic velocities as well, so not only coordinates. And for some more advanced applications, we also need forces, for example, when we want to analyze friction. So this is additional data that we need to be able to communicate through that interface. What would be nice to have, and we implemented that, of course, is to have control over wrapping and unwrapping molecules in a periodic system, so be able to turn that on and off as needed. Usually the MD engines themselves are aware of basically how molecules are broken up over periodic boundaries, and they can easily unwrap that for you. If you can easily turn that on and off, that would be great. And also something as trivial as a simulation time, you can of course reconstruct that from integer time steps. Basically, how much data did you receive? And just a simple counter, but just getting the time directly, that would be nice as well. Now, before I go on, I want to show you a little bit kind of some of the potential limits that you see, because obviously even this TCP/IP interface has bottlenecks. It's actually less dramatic than what you see here, but I will show you that in a second too. If you do things basically on consumer hardware, in my case, this is an aging iMac, basically I run a simulation on the same thing, and I have a second process that basically receives data from it. Basically, the transfer rate that I see is typically on the order of 45 megabytes per second, or 47 million bytes per second if you convert that properly. If you only communicate atom coordinates, as I mentioned before, that means 12 bytes per atom. If you want more, if you want coordinates, velocities, and forces, that gives you 36 bytes per atom. If you basically assume these two different cases, you can transmit the coordinates of roughly 4 million atoms per second, and you can transmit the full information, coordinates, velocities, or forces for roughly 1.3 million atoms per second. So if you convert that, you have a simulation, let's say, of 1 in 1,000 atoms. That allows you to basically squeeze through this TCP/IP interface 40 frames per second or 13 frames per second, depending on how much information you want. If you only want coordinates, or if you want coordinates, velocities, and forces. Now, if you compare that to the typical performance that we see for systems of that size, let's say you run it on a GPU, you get a performance of 100 nanoseconds per day. You run it with 2 femtosecond time steps. That basically generates you 478 frames per second. So that means you have to adjust your transmit frequency. You cannot transmit every single step. I mean, you can, but it will slow down your simulation, which is actually built into our interface to basically keep control of that. But really, if you basically want to use the full performance of your simulation, you don't want to reduce it, you have to reduce the transmission frequency. You don't transmit every single frame, but only every n frames. And that gives you a stream resolution of 30 to 100 femtoseconds. So this is still enough to see the whole dynamic range of all the processors that I showed you in the very beginning. So that's great. But another thing to point out is that I'm kind of lowballing here a little bit because I'm just doing this on my iMac. If you do that on your on a supercomputer or high performance hardware, the interfaces are a lot faster. So I tried it on our university cluster, for example. The TCP/IP interface there has a transfer rate of larger than 100 megabytes per second. So you easily get to stream resolutions of 10 to 40 femtoseconds for a simulation like this. So this is great. This is what our new interface now looks like. Here, the link, you will see that later again, gives you kind of a detailed kind of description of the protocol. We implemented new message types. Everything is backwards compatible with the original IMD implementation, of course. We're not going to break anything. It's straightforward to expand. So if you have ideas for new types of messages you may want to include, that is relatively easy to do. We implemented it as forks and recent releases of Gromex, NAMD, and LAMS. So these supported the original IMD interface already, so we basically just had to extend that, which was great. And in addition to that, we basically built with IMD client and IMD reader classes for MDAnalysis that allow you to communicate with these modified MD engines. This is kind of what it looks like in the scheme. So you have your MD simulation that is communicating whatever you choose, coordinates, velocities, forces, Morse vectors, and so on. And these are all optional, so you can turn that on and off. at a given frequency. It communicates it via this interface. This is the new class degenerated that communicates with MDAnalysis. And MDAnalysis is basically then able to read the data from the stream as it is being generated. And you can do whatever you want with it. These are the messages that we already had based on the original IMD interface and what we basically expanded it to in the new version. We have a handshake, we have a so-called go signal that actually starts the simulation on the server side. We can disconnect, we can kill the whole thing. This MD communication step this is a message that basically communicates forces as well. Back to the MD engine. We can pause the simulation, we can change the transmission rate, we have an error message as well. And of course, what was already existing before is coordinates were able to be communicated from the server, from the MD engine to the client, originally VMD to visualize the whole thing. And this is now the stuff that we added to it. There's a session info, which gives you now more options in terms of what information do you want to transmit. We can resume the simulation after we pause this. This is important if the simulation runs faster than whatever you want to do with it, so that you can actually say, wait a second, I need to pause a little bit and digest all the data that came through the stream. So you tell the simulation to stop, and then you can turn it back on again. As I said, that will degrade your performance, so that's not the kind of ideal solution, but this is kind of a safe option. If your simulation produces data more quickly than you can digest it, this is kind of our control mechanism to deal with that. You can also send a signal that allows you to disconnect from the simulation without stopping it. So just if you basically saw enough, you did your live analysis and everything is going well, and now you want the BMD simulation just to run kind of unsupervised, you can do that. We can transmit time, velocities, forces, and the box vectors, as I mentioned before. And that's roughly what it looks like. In GROMX, as you will see later, you have kind of a two-step process when you run a simulation. Many of you are probably familiar with it. So you have a so-called MD parameter file, which is kind of your main input for what you want to do. And here we basically have a new section that gives you options in terms of setting the communication frequency every 10 steps. In this example, do you want to communicate the simulation time, the coordinates, the velocities, forces, box vectors, everything is turned on here. Do you want to unwrap the simulation or not? Basically, do you want to make molecules whole, or do you want them to be broken over periodic boundaries? So basically, this is a very simple extension of your usual MD parameter settings. And this is what happens on the MDAnalysis side. Basically, not really new. If you're familiar with MDAnalysis, in the beginning, you have to set up a universe that requires a topology file, basically unchanged from how it's usually done. And instead of a file name for the directory, you basically have this address over here. In this case, this is just localhost. That means the MD simulation is running on the same computer. Otherwise, this would be an IP address. And then you have your port number that you basically agreed on with your MD simulation to use as a communication channel. And then afterwards, you basically have a loop that allows you to loop over that directory. And that's everything you need to do. This is all you need. So basically, this address over here and the port number is used as if this is a file name, and you basically get the data then automatically. That is all you have to worry about. The only difference is that you basically cannot go back in time. You cannot access a previous time frame unless you do something with that data that you actually stored actively on your end. This is only feed forward, obviously. So what I will show you first is a minimal demo using lamps, where you kind of see how this whole thing works. So what I will do is I will run a very primitive simulation of just a Lennard-Jones liquid, in this case just argon, on a remote server. That simulation is set up, as you will see, to communicate coordinates, velocities, forces, the box vector every 10 simulation steps. And then on the other end, locally on my iMac, I run a Jupyter notebook with MDAnalysis, and that receives that information, and it doesn't do anything fancy with it. You will see applications of actually analysis done with directories later. But for simplicity, I'm just basically printing all this information for a random atom number 42. This is the general setup. So in LAMPS, you basically have a little script that sets up your simulation and everything what you want to do with it. I'm not going to go through the details here, but essentially here you can see this is controlling the trajectory output. So as you can see over here, it's set up to actually output the information, meaning your coordinates in XYZ, only every 1,000 steps. So this is quite typical that you cannot store all the information in your trajectory. But then in contrast, this is our settings for the intermolecular or the interactive molecular dynamics protocol that we use. We beefed it up to version 3. So this is now using our new protocol, and we kind of turned on that time information is being transmitted, which usually is not the case, that coordinates are being transmitted, that velocities are being transmitted, forces are transmitted, the box is transmitted. The unwrapping I turned off because it's a Lennard-Jones system, so it's only atoms. It doesn't really make sense, but we could turn it on if we wanted to. And the transmission rate is set to 10. So not just every 1,000 steps, but every 10 steps the data is communicated. So now I will switch to show you what that actually looks like. So I'm going to share my entire screen. And exit the. Can you all see my entire screen? Very good. First thing I will do is to log into our remote server. It's called Orion. This is the directory where I run my simulations. So everything is kind of already set up and ready to go. Clean up a little bit. My last test one. So what I'm going to run is a simple script over here, which basically doesn't do anything fancy, just runs LAMPs, called LMP here, with 16 cores locally using an input file, the input file that you basically just saw. I'm messing things up right now. Okay. So this is pretty primitive, so I'm going to run this, and you will see what it looks like. Simulation starting up, and we can see that during the startup, since we set these IMD settings in there, this is ready to communicate over port 8888, and it basically doesn't start the simulation right away. It waits for you to connect to it. The transfer rate is set to 10, so every 10 steps will be communicated, but your simulation right now is basically waiting for your client to connect to it before the simulation starts. Then it will receive this kind of go signal to get things going. So now I go back to my Jupyter notebook with set up over here. First, we need to import a few things. Most importantly, this is basically our new class, our IMD reader class, which allows us to communicate with such a simulation, which is able to communicate via this protocol. Obviously, we also need to import MDAnalysis, and then a few more things to basically process the data. We have NumPy and a few things that we need for just printing information later. So let me execute this cell so that this is done. So everything is now imported. Now things get more detailed here. This is where we create our universe. You can see a few additional options, but the key part is first here, the topology data. So this is our topology file for our system. And then instead of a name for the trajectory file, which what you're used to if you're using MDAnalysis on a regular basis, this is now my IP address for this remote server, the port number 8888 that we use for communication. And here are some additional options. Basically, what is the format of the data that is being communicated? This is one thing. And a buffer size. So this is something you can modify. If you increase the buffer size, you basically give yourself more wiggle room. If your data is generating, if your simulation is generating data very, very quickly, that buffer size can fill up to 90%. After 90%, if the buffer is 90% full, we basically will communicate back kind of pause signal to the MD simulation to say, like, wait a second, we need to catch up. So please wait for us, and the simulation will just pause until the buffer is emptied. And if the buffer is kind of empty to a certain threshold, we will send back a signal to the simulation that basically resumes the simulation. So this is kind of a control mechanism that allows you to kind of, even if your simulation is running faster than you can process the data, which shouldn't be the case, but if it is the case, the simulation will basically wait for you to catch up. Here I'm just selecting basically all the atoms in our simulation, and down here we have a simple print statement that basically prints coordinates, velocities, and forces, as well as the box dimensions for this atom number 42. As soon as I execute this cell where I'm generating the universe, I'm making the connection to this MD simulation, which is running on a remote server. So as soon as I'm running this, basically the simulation will say, okay, I'm connected to a client, I'm ready to go, and the simulation will start. So I will do that now. And you will see the simulation basically kicking off over here, and the data will come out on the other end immediately. Here we go. So simulation is running, as you can see down here. You can see on this end how the data is basically arriving now on my local computer. And you can see with basically every 10 steps, the time step is 1 femtosecond. So every 10 femtosecond, we get the data. we get the coordinates, the velocities, and the forces. In this case, it's a constant volume simulation, so this doesn't change, but this is how you basically see how it works. When you go up here, you can basically see how primitive it is. It's a simple loop over your trajectory as you basically would be used to process trajectories in such a loop as normal. So just the only difference is that this is feed forward. All right, then let me cancel this. The simulation stopped, so you can also see there's no data coming out anymore. And with that, I hand it back over to Hugo.
Thank you so much, Matthias. All right, I think we have time for a quick bit of Q&A. The Q&A session will be taken by Yuxuan from the MDAnalysis team. Yuxuan, would you like to say hello?
Yeah, hi everyone. Thanks, Matthias, for the great kickoff. And before we dive into more demos from other people, if there are any questions, and feel free to raise your hand. I will ask you to unmute yourself. And also, just to avoid total chaos, please don't unmute yourself before I ask you to.
I should say as well, if you're having trouble figuring out how to raise your hand, just say in the chat, or if no one's speaking, you can unmute yourself.
Okay, so there's a question from Fabian. How does it affect simulation speed?
So I can answer that. In principle, not at all. So the simulation runs as usual. The performance of your MD code is not affected by this at all. The only thing that will happen if you communicate the data in your simulation very, very frequently, basically every step, and there's a bottleneck either on your analysis side or in your transmission side, that you basically transmit information more quickly than it actually can be pushed through the TCP/IP interface or through any network connection that you have, then your simulation will be paused in order for you to catch up. But beyond that, your simulation speed is not affected at all. These are basically the examples that I showed in the beginning, where you run things in a GPU and you basically have your, let's say, 100 nanoseconds per day that you generate for 100,000 atoms. If you look at your data, if you use, let's say, a kind of consumer hardware for your interface and you get 45 megabytes per second, if you transmit your data every 100 femtoseconds, for example, your simulation will not even feel a thing. It will run as usual.
Here's the second question. Can you turn that pause option off if the TCP/IP connection is too slow?
In that case, you can just tell the simulation not to wait for you, and you can disconnect, and your simulation will just go as usual. Yes.
So the third question, does one need direct access to the remote server when the simulation is running? What about when it's a Slurm-based job on a cluster?
Mm-hmm. So yes, you do need access to the kind of node that is running. What we usually do if we do it on our university cluster, which is hidden behind a firewall, we basically run the process that is doing the analysis and the communication either on the same cluster, which may be even the same node. In that case, you just communicate to the local host on a different node of that cluster, and you basically just have to tell it what is the IP address of the node that is actually running the simulation. So in that case, you don't usually have a problem.
So the last one is whether AMD version 3 is ready to go for NAMD. Yes,
it is. So we have it for NAMD free, we have it for GROMACS and for LAMS, and we used in all of these cases basically the most recent releases of these MD engines to implement it. You will see examples of all these three. So you saw LAMS, and you will see GROMACS and NAMD later as well.
Thanks, Matthias. So if you have more questions, feel free to put it in the chatting box or just raise your hand. if you'd like to speak out. And if not, and back to Hugo.
Thank you, Xuan. Yeah, thanks for your questions. There'll be plenty more time to ask questions towards the end if you feel like if you are still developing your questions or you feel like something didn't get answered. Okay, so now I think we have Amru taking us through some MD packages, working with the IMD client and doing some analyses on NAMD streams. Take it away, Amru.
Yeah, thank you, Hugo. Hello, everyone. My name is Amrutesh. I go by Amru, and I'm one of the folks working on this project with everyone else over here from ASU. And I'll be talking to you about a bunch of interesting stuff. So I'll just go ahead and share my screen. So yes, just related to a lot of the different questions I saw in the chat as well. So hopefully some of those would be answered in this presentation, and I hope you guys find it helpful. So thank you again for being with us here today. So I have a fancy title saying that I'll be talking about different MD engines and how they stream simulation output over to the client. But the simple boiled down version is basically I'll be getting more into the weeds of what Matthias initially started off. And so for this overall setup, we basically have two sides of the coin, one being the producer and the other being the receiver. So I'll be talking about both briefly. And with that, I guess I'll dive right into it. So yeah, I'll start out with the MD engine. So the MD engine is basically just the producer, as Matthias referred to. It could be any of your favorite MD engines, NAMD, LAMS, GROMACS, and those are the ones that we'll specifically be focusing on today. But typically, a producer is anything that produces data, and the receiver on the other end is something that receives the data. So over here, the MD engines that we'll be talking about, the three of those have been appended, and their existing code modules have been modified for IMD v3. And so they are basically compatible with the new v3 protocol. And at the same time, we have also tested those modified source codes for consistency and against the vanilla unchanged version of the code bases. So in simple language, the idea is that these modified source codes are actually working and doing what they're supposed to do. And in effect, they also have the IMD v3 functionality. And the idea, again, similar to what Matthias previously mentioned, we made sure that the overall template of the V2 protocol that was already built into most of these MD engines is preserved. And we only added the new settings and configurations that are pertaining to the V3 protocol. And before I kind of go into how we do that for these different MD engines, I thought it will be useful if we go over some terminology and what exactly we mean when we say we are trying to stream data, right? So when you think about streaming data, it's the analogy that I like to point out to is just sending information. So if you were to say send envelopes to a friend, you just send them one by one. And so we are doing something very similar. We are basically streaming or sending all these data and information that the simulation engine or the simulation software is generating over this particular TCP/IP socket that Matthias mentioned. So each set of information or each information that you send at a time step is basically a message packet. And a message packet is basically, again, as the name suggests, is just a packet of information that is being sent over to the client over the socket. And typically, a message packet basically has two different components, a header and a body. And the header itself has two variables within itself, the value and length. And the body itself is what contains the information, basically coordinates, forces, and other things like that. So the value itself basically just stores an integer, which indicates the type of message that is being sent. So for example, if you're sending, say, coordinates, it's basically gonna say that it's actually sending coordinates. And so to do that, we basically have this enumerated list that's there on this table on the right side, very similar to something that Matthias mentioned, but the idea is that you have an enumeration. So say I were to send coordinates, I would say that it's basically 2. So the value for this would be 2. And the length variable basically stores the length of the body. So how many coordinates am I sending, or how many velocities am I sending? So if I'm sending it, say, for the whole system, in this case, this value will just be n, or basically say 100,000 for the system. So again, there are these different message types, but some of them are more simpler and others are more complex in comparison with each other. The more simpler ones are basically IMD, go, disconnect, and kill. And those are ones which don't really have a body, because those are just ones that are being sent from the client over to the producer, to the MD engine. On the other hand, the other more advanced ones like coordinates and velocities, like I described earlier, would have a value, a length, and at the same time also have a body. And so say if I'm sending coordinates, it will basically just be an array of floating point vectors. So for example, if it's a 3D system, it will just be a 3n array. And one of the most special, I guess, message types is basically IMD handshake. And this is something that is established at the very beginning of the simulation, where, as you saw in the demo that Matthias ran, the system, the MD engine basically waits for a connection to be established with the receiver. And so this handshake is basically a type of message packet that is passed from the simulation engine over to the receiver. And this is done in a fashion such that it actually doesn't have any body, and the length is actually exploited to actually communicate the version number. So every time you actually run a simulation, this IMD handshake is passed over to the client or the receiver, and this also basically tells the receiver what IMD version I'm running. So if it's 2, it's the old protocol, and 3 is the new one. And the other interesting message type is IMD session info. So the idea is that inside IMD session info, we basically have in its body, we basically have different configuration settings. So this basically lets us tell the client or the receiver what kind of information to expect. So again, like Matthias had mentioned, if I just want to say send coordinates and velocities and not anything else, I would just have those as non-zero values and the others set to be 0. And these are basically set by the user, and that's kind of the way we have built these different MD engines, is to have the input files for all these different MD engines have settings where you have the ability to modify or set what information you want to be able to send from your MD engine over to your client. So this example I have over here is for NAMD. So for users who are familiar with NAMD, you generally have a typical configuration file, which is just your input configuration file. So you can just append these settings at the end of the file. And the idea is you would want to set the version number, and below that, you basically have these settings. So these settings would help you determine what information you want to send. So again, over here, I'm just setting yes for everything because I just want to send all that information over to the client, but you can have no. So for example, if you only want to send positions and you're not really interested in anything else, you can just set them to no. And similar functionality is again also available in the other MD engines. So this is again similar to what Matthias had shown for lamps, where the idea is that you can, it's a little different than NAMD, but you basically have an IMD fix command in lamps, which lets you set the port, the transmission rate, the version, and also these settings, which can be turned on and off based on what the kind of information you want to be sending. Moving over to GROMACS. So for people who are more familiar with GROMACS would know that running any simulation on GROMACS is actually a 2-step process. So it's a little more complicated than the other 2 MD engines. So what GROMACS typically does is it has a pre-processing step where it collects all the different the text files which have, say, the parameters, the topology, the structure, and so on and so forth, and compiles them into a binary file. And eventually the GROMACS executable runs that binary file as its input. So for us to be able to send all these settings, we actually have to modify one of those initial text files. So in this case, it's actually called the MDP file. And we again have those settings available inside the MDP file. And so if you have access to our source codes, you would basically be able to have those modified versions of these MD engines with you, which would enable you to actually set those settings in just a simple input file. So just pointing out really quickly, so we have the source codes for lamps and GROMACS available on GitHub and GitLab respectively. Unfortunately for NAMD, due to license restrictions, we only have a patch available. So it's basically a patch that you can download from GitHub, and the source code can just be downloaded from which we recommend you to download from the NAMD website by registering with the NAMD organization. And there are some simple instructions in the repository itself that I've added, which you can just use to patch on to the original source code, which would essentially modify your source code to have those modifications with IMDv3 built in. And with that, once you're kind of done with all of that, you can actually go ahead and compile and build your MD engines for all three of them when you have the modified code available with you. And once that is done, you are basically good to go. You have the input files that I discussed previously, which you can easily use to run your setup, and you basically have the V3 protocol ready for use. And at the same time, we also have some Docker containers available that you can use, which, so for people who are familiar with containers, so this is basically just a container image that you can pull from and directly use on any local computer or system that you want to run IMDv3 with any MD engine. So lastly, moving on, I'd be looking at the other side of the coin, as I mentioned. So I previously looked at the producer or the MD engine and how we kind of have the IMDv3 protocol implemented inside the MD engine via the input files and so on and so forth. Now, the other side of the coin, which is equally important, is basically the receiver. So in practice, by definition, receiver is, again, any program that is capable of receiving data from the IMD stream from the socket. And as Matthias had previously mentioned, IMDv2 actually used VMD, which is, if you guys are familiar with, it's a popular visualization software as a receiver. And so obviously for our purposes, we basically have a Python package called IMD client, which we have developed, which is compatible with the V3 protocol, which again acts as a very efficient receiver. And I'll talk about the actual infrastructure that lets it kind of receive data from the stream and the socket. And so going a little further into that, so I have a rough schematic on the right hand bottom over here, where the idea, again, similar to what Matthias briefly touched upon, is that once the MD engine or the producer starts sending in data is basically being sent through that TCP/IP socket, right? Now, again, there can potentially be differences in speed as to the rate at which data is being generated and pushed through the socket versus the rate at which the data is being processed or received by the receiver. So to overcome that, we basically have a memory buffer. So inside our overall IMD client setup, we have a memory buffer. So this is basically a temporary buffer where data is quickly read from the socket and stored in there. And once this buffer basically gets full, we basically use the flags that or message types we talked about previously to communicate back to the MD engine, saying that, oh, the buffer is full, so please stop sending in data because I really can't get any more data. And then once that data is eventually used, a resume signal is sent back over to the MD engine. Now, as far as the rest of the components of the IMD client are concerned, are basically the reader and the data object. So the idea is that we basically have an IMD reader class inside the IMD client, which essentially reads from this buffer instead of from the socket, and basically stores all that data into a data object. And going a little into detail about that, so we basically have an IMD reader class, which is built on the MDAnalysis reader base class. So for folks who are familiar with MDAnalysis would know that I would basically be familiar with this. And the idea is that IMD reader is basically just a type of an MDAnalysis reader. And so what this does, again, is that it's just reading the data from the buffer right into an MDAnalysis object. And that object is basically the MDAnalysis universe. And so some of you might have already figured this out, but the idea is that pairing this with MDAnalysis by actually having the IMD reader as a base class of MDAnalysis just lets you do a lot of different things, because once this data has been stored into an MDAnalysis universe, you can basically directly have access to all these different plethora of MDAnalysis functions to perform analysis. And before I kind of go into showing you how that analysis is done through a live demo, I just wanted to touch upon how and where IMD client is available. It's again a publicly available package that you can download from GitHub, and just also available on PyPy, which you can just pip install on your local computers or wherever you're trying to do this do the analysis as a receiver. And at the same time, you can also kind of do that as a Conda virtual environment and pip install IMD client inside an environment and use that for particular reasons. And like I alluded previously, as most of you might have guessed, the fact that we're using IMD client and IMD reader in conjunction with MDAnalysis lets you do a bunch of different things. So now you have the data that's being sent in from the MD engine over to the receiver, which has now received all that information, stored it in a buffer temporarily, and then eventually transferred over to this MDAnalysis universe, lets you actually do on-the-fly analysis as well. So apart from what Matthias showed you previously, where you basically just were trying to look at the information and just say output or just visualize the information, over here, you can actually also analyze that information on the fly. So to do that, I'll be basically going through a quick demo for that. And the idea here is very simple. We again have the two sides of the coin, the producer and the receiver. The producer being the MD simulation, which in this particular case would be NAMD. And again, I'll just be running this very large system consisting of a lot of different proteins and lipids forming a membrane through which some ions would be permeating. And for now, I'd not be focusing on the science of the exact system, which my colleague Hikun would be focusing on later. But the idea is that I'll just try to do some primitive analysis for the data that I'm receiving from running this system on NAMD. And as far as the receiver is concerned, I have IMD client, which would be run on a Jupyter notebook, again, in conjunction with MDAnalysis. And I would be trying to perform in situ RMSF and RDF calculations, and also visualize that live as a plot. So unlike Matthias's case, where he was trying to run the producer or the simulation engine on a cluster and do the analysis on his personal computer, I would basically be doing both on the same remote server or cluster, but essentially on separate cores. And I guess with that, I'll unshare my screen and head and all right. So if my screen is visible already, I'll go ahead and talk a little bit about the code over here that I have. So again, this is something that would be on the receiver end. So this is just a Jupyter notebook that's available inside the GitHub repository for the workshop. The idea is that we want to do on-the-fly analysis for data that's being received from NAMD. And in this particular example, I'll try to do some RDF and RMSF calculations. And to start out the code, essentially the first portion is just importing the requisite libraries. So these are basically just libraries that you would require. So I have some client-related libraries, some MDAnalysis-related ones for RMSF and RDF, and some plotting-related and some parallel processing-related libraries. And then you would actually want to initiate the analysis, basically have the system set up. So in this case, it's setting up the universe and having the topology and where I'm kind of trying to read things from. In this particular example, I'll actually be just looking at the C alpha atoms of the proteins in this particular system. So I'm just kind of selecting them from my MDAnalysis universe and then just setting up the analysis objects as well. So I'll try to not go into the weeds of this, but the idea is that I'm just using MDAnalysis to set up objects or analysis objects for the analysis that I'm trying to do over here. And then at the same time, I also want to visualize that in a live fashion. So I also have a plot set up, basically just a matplot subplot for the visualization. And eventually I have the live plotting function. So over here, I'm actually trying to do this in parallel because I have two sets of analysis that I'm trying to do. I'm basically doing the RDF and the RMSF. So I'm basically just running two separate threads over which I'll be doing both the analysis. And I'll essentially try to sync them at the end of each time step and then output them onto the plot. And that's essentially what's happening over here. So I'm just calculating the two different quantities and then just updating the plot accordingly. And this is essentially just the main program doing that, just in order. So again, I have the NAMD topology file, which is just the PSF file for my system. And I have the initialize live plotting, where I'm just trying to initialize the plot. And then eventually I initialize the analysis as well. And then finally, I perform the live plotting feature. So before I do that, I guess I'll also show you the fact that I also have to run NAMD in parallel, right? So for that, I basically have my NAMD executable ready with an input configuration file. So it just looks like any simple input configuration file, except for the fact that I have the IMD parameter settings at the end that I talked about. So in this particular case, again, I'm actually sending all the information that's possible to be sent via IMDv3. So to start off, I'll actually run the NAMD simulation. So once I do that, much similar to much similar to lamps, you guys can see that it's actually waiting for the connection to be made. So NAMD is run and it's waiting for the connection to be made. So now since that's the case, now I can go ahead and run my analysis. Let's run all these cells. Now, as you can see, I have my two sets of analyses that are updating live as the simulation is running here on the bottom. So on the top, I have the RDF for the C alpha atoms in the protein. On the bottom, I have the RMSF. Unfortunately, the RDF doesn't change a lot for this particular system, and since it's a large system and it's basically just averaging as a function of time, so I'm just adding more and more data, so it's kind of just smoothing out and just averaging out. Meanwhile, the RMSF, you can actually see the changes which are happening live, and I'll also quickly show the fact that the simulation is actually also running. So if you can see, the simulation is actually running, and all that data is just being updated live on to this plot over here. And as you might imagine, so there are a bunch of different applications for this setup, and I hope that you guys can also find something useful out of it, and probably also adapt some of these useful features into your own research. I guess with that, I'll stop the simulation. And as you can see, the analysis has also stopped. I'll share my screen. And yeah, with that, I'll pass it over to Hugo for questions. Thank you.
Thank you so much, Amru. That was awesome. Really cool to see what you can do, like especially stacking multiple analyses on top of each other. So now we have a 10-minute break. I will be. Please get up, shake out your legs, get some water. But don't go away because we've got a really fun interactive demo to do straight after the break. And I'll be here members of the team will be here during the break as well to answer any questions you might have. But your 10 minutes to get some blood back in your limbs starts now. If you have any questions or if you want to chat to the developers, you can just either put them in the chat or unmute yourself or whatever. This break time is yours to use as you wish as well. All right. By my reckoning, your break has expired or is very close to doing so. I hope you all got a wonderful cold or warm beverage of choice, depending on what time of the day it is for you or where in the world you are. Welcome back. I hope you've got your coding brains on and you're excited because we're about to do a little interactive activity hosted by Lawson where you're going to write your own stream analysis. So, yeah, Lawson, take it away.
Thank you, Hugo. I appreciate it. I'm going to go ahead and share my screen. But first, just to drop the URL to the interactive part of the workshop, just put it in the chat. All right. You guys see my screen okay? Sweet. So yeah, one of our goals with this workshop is to get you guys hands-on with the IMD client and some of the modified simulation engine code. So we went up and set a GitHub code space for you guys that has a modified version of GROMACS with IMD v3 capability, and then a Khan environment with MDAnalysis and the IMD client installed. And we're going to work up from basically just examples that I walk you guys through to some short, fun coding challenges. So all the instructions I'm going to be going through are in this repo on this README under interactive activity. So if I start going too fast, feel free to slow down and just read through the instructions yourself. But to get started, we're just going to need to get a code space set up for you. So go ahead and click this green drop-down box in the top right of the repo. And just to mention, if you guys have questions, go ahead and drop them in the chat or are having some bugs that you're facing or errors, and the MDAnalysis team will help you guys out. So once you click this drop-down box, go ahead and select code spaces on the right here. And just click this plus button, and your environment will start up in the browser for you. And you can see it's starting a VS Code instance in the browser. First thing we're going to do is we're going to open up this activity directory here and double click on activity.ipynb, which is our Jupyter notebook. There we go. Now, once we do that, we're going to go ahead to this top right corner over here, and there's a select kernel button. And we're going to select the environment that has IMD client and MDAnalysis already installed for us. So once you click that, you'll get this dialog box that pops up in the middle here. And go ahead and click Python environments. And right in the middle here, you should see with a star, this workshop environment that has everything you need installed in it. And again, if you guys are falling behind, all the instructions that we're running through are on this README page, and feel free to ask questions in the chat. So I'm going to be walking you guys through this notebook, but everything that I'm saying is written in the notebook. So if you want to speed ahead and tear through all these activities, be my guest. But the first thing that we're going to do is start our simulation. So a terminal should have automatically opened for you guys. So in the terminal, we're going to go ahead and change directory into the same activity directory. And once you do that, you're going to go ahead and do /run.sh, which is the script we provided. And just to explain what this does, all we're doing here is, if you guys are familiar with GROMACS, we're just running the GROMACS preprocessor to create our TPR file, the topology. And once that completes, we're going to run GROMACS MD run. We're going to pass in the IMD wait flags that it waits for our IMD client to connect before running the simulation. And we're going to pass in just an IMD port of 9999, something nothing else on this machine is using. And just to note here, this is just a simple CPU build that's only running on a CPU of GROMACS, but you can, of course, build this to work on a GPU or with more advanced options like MPI. So I'm going to go ahead and run this script. And we can see the preprocessor is running. And the simulation has started. So we will know that our simulation is ready once it has printed to the terminal and says IMD will wait until I have a connection and IMD go orders. So this first cell that we're going to run here, I'll just explain this line by line. A lot of this is just boilerplate code. So first thing we do is import the reader so that MDAnalysis knows about it. Then we, of course, import MDAnalysis. And we create our universe. If you guys aren't familiar with MDAnalysis, this is just our object that's going to tie the topology and the trajectory together. So we're passing in the CRO file, which is our topology, passing in the IMD URL, and setting a nice big buffer size so that things go smoothly. Then we have this atom selection line right here, which is going to use the universe object to get a reference to just a random first atom in the topology. We are printing a header file and then running our analysis loop. So in nearly all MDAnalysis analysis code, you're going to see something that looks like this. All this is doing is iterating through the trajectory from whatever backend, in this case via IMD, and loading in simulation frames one at a time into this time step object, which is going to hold things like the simulation time, the position, velocity, force, and dimensions. So one thing that might look strange here is that we're accessing the positions not through the time step, but through the atom. But this is something that's possible in MDAnalysis because as you're iterating through the trajectory, the atom is referencing the time step underneath the hood and updates as the time step updates. And then at the bottom here, this code, just as a best practice, we're catching any exception that might be raised, and we're going to go ahead and close the IMD reader, which we're referencing through u.trajectory to make sure the socket gets shut down. So I'm going to go ahead and run this. And you can see we have information being printed live about the simulation as it runs. Now, we don't have to restart the simulation after running each cell. To make it easy, you can just go ahead and press the interrupt button here or here. And the simulation or the client will disconnect from the simulation and wait for another client to connect. So just make sure to do that between running each cell. So this print statement is nice, but it's not a very realistic use. So we're going to start doing a little bit of analysis. The first thing that we're going to do here is we are going to just simply calculate live the distance between the N terminus and the C terminus of the simulation. So should have mentioned before, the simulation is just a protein in water. The PDB URL for the protein is at the top of the notebook. But all we're doing here is just simply selecting the N terminus, which has a res ID of 1 in the topology, and the C terminus. And you can see we're selecting the alpha carbon of each one. So all the rest of the code has remained the same, but now inside of our analysis loop, we're going to calculate the distance between their two positions and just print a simple statement that tells us how far apart they are at each time in the simulation. And as we run it, you can see it tells us the time in picoseconds and how far apart the N terminus and C terminus are in angstroms. So I'm going to go ahead and stop this cell. Now, one thing we might like to do is instead of just simply printing a result, is have a cool graph that shows us the results live. So we went and provided just this simple graph utility for you guys that just allows you to have an updating scalar on a graph. Just talking through the arguments we're passing here. This is the time window. This is basically how wide the x-axis is going to be, how many times it's going to show you. dt, this is the dt of the simulation. And then just some descriptive information passed in through these keyword arguments. And all the rest of the code is remaining the same. So I'm going to go ahead and hit run. And you can see in our analysis loop, every time we calculate a distance, we're simply calling the graph update method, which passes in the current time and the current distance between the N terminus and the C terminus. And we get this graph here. So you can see it live updating there. I'm going to go ahead and stop this one. So another very common thing that you might want to do is write only a subselection of your trajectory. So this simulation is a protein in water, but say, for example, we only wanted to write the trajectory of the protein molecule to the disk. We can do that with the IMD client. First, what we do is using the universe object, we select all the atoms in the topology that are not water, since the only non-water molecules in our simulation are protein molecules. Then we create our writer object. Typically with the writer, you'd pass in universe.atoms.natoms, but in this case, since we're only writing a subselection of the entire trajectory, we are passing in the selections number of atoms. And then this same loop that you guys have been seeing again and again, just writing all the atoms, their information to this protein.tirr file. So one thing you might notice that's unique is we're not specifying the length of the trajectory. This is because the IMD client doesn't know how long the stream is going to go on. So by default, what this is going to do is the client will determine when the simulation has ended. And in that case, it will flush whatever's written to disk and complete writing the trajectory. But what we're doing here is just simply setting the desired length of the trajectory and breaking the write loop at 10. I'm going to go ahead and run that. And you can see in our sample simulation folder, we have a new protein TRR that got written. All right, so now that you guys have seen a couple examples of how this works, we have a fun challenge for you guys. The first one, a little more simple. The second one requires implementing an algorithm. So just to start with the first challenge, using the MDAnalysis selection language is to implement an analysis function that calculates the number of water molecules that are within 4 angstroms of the protein during each time step. And if you want, you can go ahead and use this graph utility that we provided to create a live visualization of this data. So what I'm hoping we can do is just give you guys sort of a quiet 10 minutes to work on this. And I will leave my screen on and start working on it slowly. We have all the tips and all the syntax you guys will need to solve this problem right here, and some template code down here that you just have to fill in with your analysis code. So with that, I'm going to go ahead and mute myself and give you guys a chance to work on this challenge. If you guys get stuck, we have the Atom selection language documentation page linked here. And we also provided a solutions Jupyter notebook to each challenge if you get absolutely stuck. All right.
I'll just add as well that if you're stuck, feel free to ask in the chat or unmute yourself and say, hey, this is what I'm struggling with. Just let us know, and a team member will come and help you.
we came up is we are selecting all the atoms, which are water molecules, and they are within 4 angstroms of a molecule that is not a water molecule, which must be a protein. And then we're just setting that to updating equals true to recalculate what that group is for each time step. Then we can select the length of this group to get the number of atoms. So our next challenge is going to be a little bit trickier, is to find the radius of gyration of the protein for each frame in the simulation. We provided the analytical formula here. So in this representation, you don't need to find a separate radius of gyration for each axis. We're combining the axes into just one distance. And we show how to do that down here in this sample code. So with that, I will send you guys off again. We have a link here, which has a very similar method that you guys can use for inspiration. And again, in the Solutions Jupyter notebook, you can see a working solution if you would like to cheat a little bit. And I'm going to go ahead and go on mute. Again, feel free to ask your questions in the chat.
Once again, when people have working solutions, I'd love to see them in the chat, or the plots, or some plots, just some numbers, some plots, whatever. We have a few people's results rolling in. What do we have from our MDAnalysis maestros? Seems like we might have a consensus emerging.
All right, looks like it's been around 10 minutes. So in this solution, I'm just simply using the radius of gyration method built in. I appreciate all you guys participating in the activity and sending your solutions in the chat. We really wanted to have you guys try out some of our software and start thinking about maybe some of the more advanced analyses and visualizations that you guys would be able to do. So with that, all of this code is available in the repo, and you'll still be able to access it, all this example code after the workshop, and I will hand this back to Hugo.
Brilliant. Thank you, Lawson. I believe I'm handing it straight back to you to look at some of the MDAnalysis side functionality. Would that be correct?
Yes, that's absolutely right. Let me share a different tab here.
And thank you all for participating in the interactive, as Lawson said, for participating in the interactive portion of the workshop. We thought it'd be really valuable for you guys to just actually give it a try.
Give me just a second here. All right, is everyone able to see my screen? Sweet.
Yeah.
Okay, so now you guys have actually had a chance to use the IMD client and the modified simulation engine. Wanted to talk about sort of our philosophy of development, the features that we added, why we built things the way we did, and then some of the more advanced features that you can use. So first, to talk about the overall architecture of the package, we basically had 3 priorities when we built this. Number one being, even though we love and are very excited about MDAnalysis, we know everyone else might not be. So if you're a developer that's interested in using IMDv3 in Python, but you don't want to have to use or install MDAnalysis, the IMD client itself that interacts and speaks the IMDv3 protocol is totally usable without installing MDAnalysis and without using it. The second principle we wanted to kind of follow here is, we want to have the definitive client for IMDv3. So we tried to take a batteries included approach as much as possible. So you guys will see later, we have lots of error handling, lots of cool different features, and then some automatic things that are going to be done in the background for you as you use it. And then finally, for the MDAnalysis components of the IMD client, we wanted to strive as much as possible for a user experience that's similar to how people are already using MDAnalysis. So we want the trajectory reader to feel like a trajectory reader, and we want to be able to use built-in analysis classes exactly as people did before. And in the cases where we can't, we want to make it fail out in a very obvious way. So with that, you can see we have the overall architecture of the package here. The very core part is the IMD client itself, which is the part that interacts with the socket and the simulation engine. Then the IMD reader is a wrapper for that is an interface into MDAnalysis that allows it to act as a trajectory reader. And then finally, the universe object. As I said before, this is like what ties the topology and the trajectory together in MDAnalysis. So this very core part, the IMD client, has a very, very simple interface, literally just 3 methods. One, get IMD session info. This will just tell you what data is going to be present in the stream. 2, get IMD frame. This is just going to give you a simulation frame with whatever the IMD session info told you were going to get. And then finally, stop. This is just a shutdown method to keep everything clean. Typically, this will be handled with a context manager, as you guys will see. So just very basic code that you might be writing as a developer. We are using this context manager with the IMD client class that we're setting up. Just simply pass in the host, the port, and the number of atoms. This is we have to pass in the number of atoms explicitly, just because MDAnalysis can't parse it from the topology in this case. Then we're calling get session info and printing it, and you can see it tells us the version that we're using, the endiness of the simulation engine machine, and then just some metadata basically about the simulation stream, telling us we're going to receive time, box, positions, velocities, and forces. Then this other method we call get IMD frame, and this is fairly similar to an MDAnalysis time step, where it's an object that essentially just holds some scalars and some arrays. And we can access that information through frame.step, frame.time, and frame.positions, very similar to how we would with a time step. So realistically, if you're a developer, you're going to be writing code that looks a bit more like this, where you are iterating through the trajectory. So exactly the same code as before, except now we have a while loop that just infinitely repeats through the client stream and continually calls get IMD frame. And just like with any kind of file object, whenever it's over, it'll just raise an end of file error that you can catch to stop your code. And ideally, obviously, you'd actually be doing something with the frame data that you're pulling here from the client. One thing to note here is, the API is extremely simple since you are interacting with a simulation that goes in one direction. So you are not able to slice the stream or do anything that you would like with a NumPy array, for example. Oops, I am inside of this code box here. So we've added a little bit more advanced options for different use cases here. First one being, if you're in a high latency situation where your simulation engine is executing somewhere potentially far from where your analysis code is executing, you don't want your client to just think the simulation is over when it's just slow. So we have this timeout option you can set. And in cases where your simulation engine is running much, much faster than your client analysis code, you can set a buffer size to give yourself a little bit of wiggle room and make sure that TCP isn't just sending the same packets over and over without them being received by your client. So just to talk about how we're able to implement a buffer here, just very briefly, we're going to dive into the architecture of the IMD client. Now, the exact mechanism of how this works is not important, but what is important is there's a client-facing thread, the IMD client, that I was showing you in the previous examples, and then it will start up on the back end a producer thread that's going to interact with the socket for you. So at a very high level, how this works is this producer thread is going to continually get some free memory from this interface buffer. It's going to fill it up with information that it got from the simulation engine, and then it's going to make it available for you to use via get IMD frame from this client. Now, because we have this architecture, it allows us to do some cool stuff. So, for example, we can do some automatic pausing and resuming in cases where the simulation engine is running much, much faster and filling up our buffer. So just a quick example here, we're passing in a ludicrously small buffer of just 2 megabytes. And I'm going to go ahead and execute this code here. And you can see over in our GROMX client over here, whenever our buffer fills up, this producer thread is automatically sending a pause and a resume signal to our simulation engine so that the buffer does not get overfull. One thing to note here is there's, with this automatic pausing feature, there's absolutely no change for you as a user. Everything looks exactly the same. All right, so now you guys have seen the inner workings of the IMD client. I'm going to talk about how the IMD reader wraps it and what you can expect from it. So like I said before, you can't slice a IMD stream since it only moves in one direction. And So the reader has the same limitation. It can't be sliced. You can't specify a start or an end frame, and you can't go backwards through it. And just to explain why that's the case, your code, you're calling some kind of analysis loop here with for TS and U.trajectory, which is trajectory is just a reference to this IMD reader object. The IMD reader object for each iteration is going to make a call to the IMD client with get IMD frame. The IMD client is going to return an IMD frame object, which the reader converts into a time step and gives back to you. So you can use this common MDAnalysis interface. And just to show what these limitations look like in practice, since a simulation only runs once and you can't just simply restart it with IMD, in this code, we are iterating through the entire trajectory. And if we attempt to iterate through a second time, it'll go ahead and raise a runtime error and tell us that a stream is not a file, so we cannot slice through it. So to give a more comprehensive understanding of what you can and cannot do with the IMD client and the IMD reader, all of these are okay since we're simply iterating forward through the trajectory without specifying a start or an end frame. We can also specify a step between the frames that we look at. But if we try to do any of these things, we're going to raise a runtime error since we don't know if we're going to reach a frame 10 in a stream. We don't know if we're going to reach it, so we don't know if we can start with that frame, and we can't go backwards in it, and we definitely can't ask it its length using length of U.trajectory or U.trajectory.end frames. So with these limitations, we have strived as much as possible to make the IMD client compatible with MDAnalysis analysis classes, but there are a couple caveats. First one is we can't handle a trajectory. We can't use analysis code that requires the length of the trajectory. So not all MDAnalysis analysis classes are going to work. And second, since the analysis base class asks for the length of the trajectory, we have to patch it in with a monkey patch whenever you import IMD client. This will happen automatically, but it's obviously not an ideal coding practice. So we are working with MDAnalysis developers to make sure that our patch gets into the main code base. So just to show what this looks like, Amru showed you guys some RMSF code earlier, but just a very simple example. We're creating our RMSF class and running it, and you can see it runs using a trajectory via IMD. So one difference with IMD is in a typical trajectory, you can just simply reuse your trajectory as many times as you'd like to run as many analyses as you like. But since with a simulation, you only get one chance, you have to run everything on the same loop. So if you are packaging your code into different analysis classes, we provide this stackable analysis class that takes an array of other analyses as an argument. So after you create your normal analysis classes as you typically would, you pass in this array and then call run, and you can then access the results of the analysis just like you normally would with RMSF in this case. And that's all I got. I hope you guys are excited about using this package, and if you have any questions, let me know.
All right, thank you, Lawson. We've got a quick 5 minutes for some Q&A before we get into some demos of some fantastic scientific stuff. So I'll open the floor and chat to any questions. Seeing as we didn't have the chaos that we anticipated, we feel free to just unmute yourself if you would like to ask a question. We have a question from Gareth Elliott. How involved is the server-side code in the MD engine?
Yeah, so this is something that we were really excited about, is that IMD v2 was already implemented in all of these different MD engines. So realistically, we're just taking existing methods and classes and modifying them slightly. So really not a huge change.
Fantastic. Last chance to ask any questions. Well, not your last chance, but if there's no further questions, maybe we'll move on to some scientific applications with Hikun. Hikun, do you want to take it away?
Yeah, thank you, Hugo, for passing the torch. Hello, everyone. My name is Hikun. I'm a member of the Haydn Lab and also one of the contributors of this project. And today I'll talk about some applications where our methods can be useful. So, sure. Okay. So the first application I'll talk about is that we can use our method to study the molecular vibrations. So one of the methods to study them is using the infrared absorption spectroscopy, where it's able to detect the vibrations involving changes in dipole moments. However, due to its selection filter, it is only able to detect some vibrations. Another method that we can use to study the molecular vibrations is actually by describing the vibrational density of states using the atomic velocities. So with this method, we can actually detect all vibrations occurring in our system. And we can do that by analyzing the fluctuations of velocity using the time correlation function, as you see over here. Now, if we Fourier transform that correlation function, we can describe a VDOS. And what's really useful about VDOS is that at the zero frequency, it describes the diffusion coefficient and also the shifts in vibrational peaks containing thermodynamic information, such as if the peaks are shifted towards the higher frequency, then the force constants become larger, therefore the entropy is lower. On the other hand, if the peaks are shifted towards the lower frequency region, that indicates that the force constant is smaller, thus entropy becomes higher. What we also can do with VDOS is that if we normalize it by the average kinetic energy, we can determine how many vibrational degrees of freedom are contributing to the kinetic energy at each frequency. And in the end, if we actually integrate the total VDOS, we can know how many degrees of freedom we have in our system. And as I just mentioned, the shifts in vibrational peaks contain thermodynamic information. But how do we actually quantify that information? We can do that by applying a method called two-phase thermodynamics, where the VDOS of liquid is represented as a superposition of two analytical models. So the gas-like phase of liquid is analyzed using the hard sphere fluid model, which describes the zero frequency and the relaxation dynamics. The rest of the VDOS, which is more of a solid-like phase of liquid, can be analyzed using the harmonic oscillator model. And with this method, an example, we can get the entropy of liquid by So we can do that by using analytical methods to describe the entropy of both gas and solid-like phases. And in the end, if we sum them up, once we have the entropy of both phases, if we sum them up, we can get the entropy of liquid. So on the figure on the right, we can see the entropy density of water. So as I mentioned in the earlier, in the lower frequency region, we can see that the entropy is high. And as you go towards the higher frequency, the entropy decreases. Now, I want to mention that one of the specialties in the Haydn lab is using the 3D 2PT method, where we analyze the VDOS in 3 dimensions and compute the changes in solvent entropy and free energy around a solvator molecule, such as a protein. And now I will move on to showing you how our demo works. So just share entire screen. Go. So right now we are in our computer cluster, which is called Orion. So what I'm gonna do right now in the live demo is that I'm gonna run the simulation on a computer cluster, but we're actually going to run the analysis on our local machine. So just to give you a quick look of the simulation we're doing is we're going to be using GrowMax for the simulation. And this is the pre-processing step, and we will be using a total of 12 cores to generate the simulation data in port number 8888. Now, if we run the simulation, so right now, since we gave the IMD wait flag to GrowMax, it is actually waiting for this go signal to start the simulation. So I'll move on to the Jupyter notebook where the analysis is performed and where we can actually visualize the VDOS. So in the first cell, we import all the necessary libraries that we need. So all the packages from IMD client and MDA. Also, we're going to import NumPy to store our data. And we also have to import the VDOS library in order to compute the time correlation function and describe our VDOS. And then the 2 libraries you see are down here are simply for the visualization. So just make sure that we load the libraries. And on the second cell, you can just see the settings for our figure. So if we run this, you can see we just have an empty plot because we are not actually running any simulations. So here on the third cell, we create the universe using MDAnalysis. So we give in the topology file, and in order to establish a connection with the MD engine that's running on our cluster, we give the IP address of our cluster, and as I previously mentioned, we use the port number 8888 to make a connection between the MD engine and the reader. So here we're selecting all water molecules, and over here using the VDOS library, we are using the last 200 transmitted frames to compute the time correlation function. In this line of code, we are using a total of 4 cores for our analysis, and we're performing this in parallel. And over here is where, in this loop, is where we store the data for our VDOS and display it on the plot. So I'll just run this cell, and once it's running, you can see that connection established and the simulation is actually running. So right now the simulation is running, but we don't really see anything yet because there's nothing to be updated. But just to let you know, the transmission rate currently is 8 femtoseconds. And as I said before, we're using the last 200 transmitted steps to describe the VDOS. So therefore, you could have noticed already, the plot will get updated every 1.6 picoseconds. Now we see there are two lines in our VDOS, which the blue line represents the total VDOS that is averaged by the total number of water molecules we have in our system. And in the orange line, we're describing the VDOS of a single water molecule in our system. So as you can see, the blue line, since it's averaged over all water molecules, from the beginning of the simulation, we already see that the line is already kind of smooth and kind of converged. While before the VDOS of the single water molecule was actually very noisy, but as you run the simulation long enough, it's going to keep exploring all the spaces and eventually become more smoother. And you already see that the shape of the single VDOS is looking more similar to the total VDOS. And as you can see over here, we sometimes get the pause command and the resume command because the buffer is getting filled up. So the data is being generated faster than being analyzed. So we need some time for the buffer to clear out before we analyze anything. And yeah, as we keep running the simulation, you can see how the plot of the single VDOS is looking more similar like the one of the total VDOS. So I'll stop the simulation for now. And if you have any questions, please feel free to ask during the Q&A session, and I'll be more than happy to answer. Now, I'll move on to the second application that our method can be useful for. So ion permeation through membrane is a process which is known to facilitate biological processes such as cell communication and signaling. And there's a lot of research being conducted to measure the current during this permeation events in order to gain a further understanding on how the flow of the ions are regulated. So if one wants to run a simulation of such process, then they would have a single membrane under the periodic boundary condition. And for example, if the ion is initially starting from this position, and in the next time frame or in the next couple of time frames, if you see the ion ending up in this position, we can't really determine how it went to that place. What I mean by that is that the ion could have actually permeated through the membrane and reached that position, or it could have been just a diffusing ion and its periodic image just happened to appear in the same position. So using one membrane, unless we have a high time resolution, using one membrane has some limitations of its own. So what one would do to overcome this limitation is running a simulation with two membranes. So if we have two membranes under the periodic boundary condition, what that will do is create this two distinct compartments. For the sake of the talk, I'll just refer to as some inner compartment and an outer compartment. So using the same example, we have an ion initially at this position, and in the next time frame, if the ion ends up in the inner compartment, then we can actually distinguish that this ion permeates through the membrane as it's the only path that it can take to reach that position in the inner compartment. However, but also if the ion is diffusing around in the system, then it will just end up in the same compartment as an example that you can see in the dashed line over here. So with this method, we can actually distinguish the ions that are permeating and not permeating. However, the system size just becomes much larger than what it was previously. And it just takes too much computational resource to run these simulations for a long time at a high time resolution. So to give you a better idea of how it would look like in a real system, we have a membrane pore of MSPA. And I would like to especially thank Dr. Chris Maffeo and the Aximentiev group at Urbana-Champaign for providing the script for the analysis and also the simulation data, as well as providing the idea for the application of our method. So over here in the cyan color, we see we have the membrane pore. The purple spheres are the potassium ions, and the green spheres are the chlorine ions. So as an example, if we're trying to check whether this potassium ion permeates through the membrane or not, if in the next time frame, if it's ending up in the bottom side of the membrane pore, we don't actually know if it actually permeate through the membrane or if this ion just happens to be a diffusing ion in the system and it just ended up over there in the bottom side of the box. So in order to actually distinguish whether the ions permeated or not, when using only one membrane under the periodic boundary conditions, we need super high time resolution in order to track the z-axis position of these ions. And what's useful about our method in such studies is that our method is actually able to track the z-axis positions of these ions as the simulation is running, and we can compute the currents based on the position of the ions in the z-axis. So for this application, I will also show you a demo for it. So the way I will run this demo is that I will run the simulation on the cluster and also the analysis on the cluster side as well. So we just do. So, oh, and just to mention, we are using NAMD for this live visualization of the current. So right now, we're connected to NAMD. So we're currently using a total of four cores. And just like GrowMax, it's waiting for this connection for the go signal. And once it's waiting for the connection, we'll go over to the Jupyter notebook and we import all the libraries we need. So we import the IMD client, IMD reader, and the MDAnalysis library, and also NumPy and all the libraries we need for the visualization. So we run that cell. And over here, we're generating the universe using the topology file. As you can see, that's defined over here. And as I said, we're running the analysis, this Jupyter notebook on the cluster as well. So we don't need to change the IP address. We can just refer it to as localhost. And we will be using port number 9918 to establish a connection between NAMD and our Jupyter notebook. So over here, we just have the commands to set up our plot. And the X data, we're going to store the simulation time steps. And on the Y data variable, we're going to store the current as the calculated current as the ions are moving. In the time step, this is the time step that is defined in the NAMD parameter file. Frame diff is the variable for that describes the transmission rate of our method. So we're going to be transmitting data every 1 femtoseconds. Here we have the charge factor that we need to calculate the current. And also, we're going to be tracking the z-axis positions of only the potassium and chlorine ions, just like the example I showed you in my slides. And we can actually extract the z-axis position using this command line over here. And in the loop over here, we're we're calculating the current at each time step for both the potassium and chlorine ions, and we're going to be able to visualize that with our method. So before we run this Jupyter notebook, let's make sure that our port number is correct. So it's waiting a connection on 9918. It matches, and if we simply run this, so you can see that the ion current is being calculated for every time step as we are tracking the z-axis positions of the potassium and ions. So in this simulation, we're using an electric field of 150 millivolts. And the current that we see here are generated by the movement of the ions. So because the ions are moving right now, we can get these currents calculated. And what's really special, or what's the advantage of our method, is that we can actually track these at really high time resolution. So usually one would use a larger time step in order to either decrease their computational resource in order to run longer simulations. However, the problem that occurs with larger time steps is that we can't see those fluctuations that we are observing right now at a high time resolution. So rather than seeing those fluctuations that we're seeing right now, if you use a large time step, it will be averaged over, and you might see some like small fluctuations, or even maybe even straight lines in worst cases. So I just wanted to showcase that with our method, we can actually track the z-axis positions of the ions to measure the current, and we hope that our method provides another step forward to understanding the dynamics of the ion permeation through the membranes. And I'll just stop the simulation for now. And yeah, so just to let you know, all of these demos are available in our GitHub repository, in the workshop GitHub repository, and also on the agenda, I believe there's a link to it. So if you want to run the full simulation on your own with these live visualizations, please feel free to download the Jupyter notebooks that are available on the repository. And this will end my part of the talk. And thank you so much for listening. And I'll take it back to Hugo now.
Thank you so much, Hikun. Those are really, really cool scientific applications, at least in my opinion, of streaming stuff, showing like the really unique things that you can do. So we've got 5 minutes for Q&A. Does anyone have any questions on the stuff that Hikun presented? Don't be shy. Question from Alex. Is there a way of starting the analysis without having to wait for a Jupyter tab to be run?
As far as I know, we will have to give the wait signal to actually perform the analysis, because if we don't give the wait signal, then the simulation will just simply start running on its own, and then we won't really have any data coming in through the socket. Oh, yeah, the simulation, yeah. Yeah, so we do have to give a wait signal, or else the simulation will start on its own, and we're just simply losing all the data that could be actually useful for analysis.
Yeah, so I just want to jump in and say, do you mind muting for a second?
Oh, yeah, sure.
So that's actually a configuration option that we have on all the different simulation engines. You can decide whether or not the simulation will wait for an analysis client to connect, or whether it'll start immediately and a client can connect at any time. So if you're interested, for example, in just monitoring the state of a simulation, but you don't need every single frame and you want to jump in sometime after the simulation has started, that's an option that you can see the options at the bottom of the IMD workshop repo on how to do that.
Fantastic. Any more questions? I'll give you 30 seconds or so. Alrighty. Well, if there are no further questions, I think I will pass on to Matthias, who is going to take us through some future directions.
Yes, thank you very much. Let me share my screen. There we go. So what you've seen so far is kind of what we implemented as the kind of current version of the version 3 protocol for IMD, which allows us to communicate coordinates, velocities, forces, the box dimensions, and so on, and all the options that you have seen. If you want to read more about the full description of that protocol, you can see that under this link. You can also see the link here under this QR code if you want to look at that. So basically, Lawson has documented there in great detail kind of what is defined in this protocol, what kind of messages do exist. And you can also see in there kind of how kind of straightforward it is to expand that. A few things that we have been thinking about what we could do on top of all that is something that basically builds on what already is possible at IMD version 2, basically to communicate forces back to the IMD simulation. The only thing that you have to basically ensure when you do that, if you want to use it for some applications such as enhanced sampling simulations, is that the forces that you generate kind of stay in sync with the simulation, that they're kind of communicated back exactly at the right time. But that can be done in principle. So what allow you to do is basically to evaluate, let's say, collective variables that describe the state of your simulation. Based on these collective variables, you apply a biasing force to kind of push your simulation a certain way. Let's think about, for example, about metadynamics, and then to kind of run your simulation in this kind of biased way, very similar to what you would usually use Plumed, for example, for. So then instead of Plumed, you would use an MDAnalysis notebook to do your analysis of these collective variables, generate your biasing forces, and communicate things back. So that would be one thing one could do. Another thing one could think about is to allow not only quick communication of forces back to the MD, but also to modify atom coordinates, velocities, or even the box information. So what would that allow you to do is basically to implement this interface of MDAnalysis or some other code. As Lawson pointed out, you don't need MDAnalysis. You can just use your IMD client to kind of communicate with any other program that you can write. You could use that as a kind of simple implementation to do hybrid Monte Carlo, where you basically run an MD simulation, and every couple of steps you also implement some Monte Carlo steps in there. So that would be one way how you can use this. You could also use this basically prototype new thermostats or barostats, where you basically modify velocities of a box in your system using some analysis script that you run. Probably it will not be super fast, but that way you can prototype new things very quickly. So that's another thing we are thinking about. Something that came up in the questions in the chat is to do multiple parallel streams. That when you basically run a simulation, that you can connect not just to one Jupyter notebook that someone runs somewhere that does some analysis, but multiple, possibly communicating all your data via different streams using different parts. So that's one thing one can think about. But since we have you all here, more importantly would be what you think this is interesting for. So if you have any ideas how you would implement this kind of interface in your projects, especially development projects for new kind of things that you plan to do, would be great to hear from you. So this is, I think we have a Q&A afterwards, so basically kind of give you the chance to weigh in. But of course, you can reach us anytime as well to Like if you have any ideas what else we could do, what else we could implement into this kind of protocol to make possible whatever you are thinking about, that would be perfect. Then I'm giving it back to Hugo.
All right. We have 20 minutes for an open forum. So again, this is your chance to have your say in the future of IMD v3 and say what you liked, maybe what you didn't like, what you might change, what cool scientific applications you have that you'd like to see streaming applied in. And now's your chance to discuss with each other, with the developers. Please just feel free to unmute yourself or ask any questions in the chat.
I'm going to just ask a question. Of course, I'm involved in the project, but so just to give other people some time to think. So I think there was a question about, is this available in D3? And I think Amro already answered that you can get the patch. But I think more broadly, I think an immediate question is, can I just use this in my favorite MD code? Or if not, what has to happen so that this becomes a possibility?
So at the moment, you would basically have to recompile your favorite MD code using a modified version of the code that we have in our repositories. And that's right now limited to Iron MD, where you can use our patch to update your source code, Gromex or LAMPS. We are currently, in one of our next steps is basically to work more closely with core developers of all these MD engines to make that part of their future releases. So that's something that we are certainly pursuing, so that basically in the future, ideally, that you basically just install these MD engines as you usually would do, or you have your system administrator do it, and all these options are already included. That is currently not the case, but that's hopefully something that we can arrange with the core developers of these MD engines in the future.
Yeah, just one thing to add is, in addition to being able to compile the code with our changes, we also make some Docker containers available with the LAMPS and the Gromex already compiled for if you have a relatively new NVIDIA GPU.
Yeah,
but we're not able to do that for NAMD quite yet.
That is correct. That's something I forgot. So the Docker images allow you to basically to use them as is, which is a lot easier than compiling the code yourself.
And I guess as for, I'll just quickly jump in, as for other MD engines, I think it really depends on, firstly, the language in which it is written. For example, OpenMP, it's a little easier since it's we have almost all of the tools already written for IMD client, like Lawson had previously mentioned. But for some of the other MD engines, it really depends if they actually have access to the TCP/IP sockets built in already, or if we need to kind of make that happen. So I know that in whomdblue, the setup is a little different, and they kind of got rid of, I think in one of their more recent releases, got rid of the access to TCP/IP sockets, and they have a different buffer system within itself. So again, for any MD engine to have this functionality, it really just depends on the kind of infrastructure or like the code architecture that they have.
Yeah, it's pretty straightforward to do for any MD software that already supports interactive molecular dynamics. I think that's what Ambro just mentioned. whomd used to do that, and they are not going to do that in the future. But any other software that already supports interactive molecular dynamics as it was conceived basically close to 25 years ago by John Stone, that is relatively easy to expand. But yeah, we have done that work for you already for LAMS, NAMD, and GROMACS.
Question from Noah. Is it possible and safe to end a simulation from MDAnalysis after a variable is calculated as converged?
Yes, you can actually do that. If you really want to end the simulation, not want to continue in running, as soon as you disconnect, the simulation will automatically pause. And you can also send a kill signal in principle. I don't think we have tried that yet, but that is in principle implemented to basically tell the simulation to just stop when your data is converged. So that is part of the protocol already. Right now, if you don't send, so you can send a message to tell the simulation to continue running after you disconnect. If you don't do that and you disconnect, the simulation will just stop and basically wait for a new connection to arrive unless you actually send the kill signal as well. But yeah, in principle, this is all possible. So one thing that comes up often and that you saw a little bit in Hee-Koon's presentation, when you want to compute something like time correlation functions, you need to store the history of your trajectory. So the reader obviously is feed forward, so you basically get the simulation data as it comes in. If you need to do an analysis where you basically need information about the history of the recent past in your simulation, you basically need to store that. And that's something that you can easily do. You can basically store your data in NumPy arrays and then manage that and basically update that whenever new data comes in. So the presentation that Hee-Koon showed where he calculated the vibration density of states using a time correlation function was essentially doing that. And what we are currently doing is to develop basically a number of different MDA kits that support that as fast as possible. Like basically what you need is to be fast. You want to be basically as fast as the simulation runs as well. And if you run things on GPUs, that means that you want to be really fast. So we are kind of implementing C++ libraries that you can call within MDAnalysis that basically do these kinds of things for you.
Question.
Mm-hmm.
A question about alchemical free energy applications for streaming. I'm gonna perhaps throw this between Oliver and Matthias. I know Oliver does a lot of free energy calculations.
I guess that goes a little bit in the direction of what I mentioned with enhanced sampling. Alchemical free energy different calculations are a little different. It's not something that we have thought of directly. Not sure if maybe Oliver has a better opinion about that, if this is something that you would use for that.
So I don't think that we have anything really planned. However, you can principle use it to decide if you've sampled enough. I think because we can communicate energies and that may have the information that you need. I'm not 100% sure actually. But one common question is how much available computing resources are you going to spend on your enhanced sampling? And if you use the IMD protocol to sort of constantly probe your simulations and ask where they are and if they've done enough, then you can, in principle, at least implement workflows that, only use as much resources as needed. But, this is, I would say, more for our future. We really don't have anything to directly support that kind of approach. But I think what should have come across is that by opening up access to important data in the simulation through the IMD protocol, you can suddenly do a lot of things that otherwise would require you to dig deep into the actual code itself. And as Matthias mentioned when he talked about prototyping new thermostats, I think a lot of value is simply there that you can quickly try out things. And if it turns out to be really good, then you can worry about performance later and then see if you can do this in a clever way. But it's sort of a little bit like open heart surgery on a running simulation that you can do.
There's another question in the chat about precautions that would be necessary, for example, if you have an analysis script that crashes to avoid data loss. So what would happen? So technically, no, I don't think there's any additional precautions necessary, because if your analysis script for some reason halts or basically stops doing stuff, your buffer will overflow, and meaning your buffer will fill up, and if it's at 90%, basically it will be communicated back to the MD engine that wait a second, we are not getting, we're not kind of up to speed, and the simulation will just pause and wait for the buffer to be emptied again by your analysis. The only thing that may require, and I think this is already implemented the way Lawson does it, is that your analysis and the communication with the MD engine, these are two separate threads. So that I think should already allow, even if your analysis thread kind of stalls and doesn't continue forward because it's kind of in an infinite loop, that the Lawson can probably say more about that the other thread is already able to detect that the buffer is full and can communicate to the MD engine to pause. Lawson, is that correct?
Yeah, that's exactly right. So just a couple of things. So for example, if your analysis script crashes, that main thread of execution is going to let that socket management thread know that it has crashed. And so you can either configure it that the simulation engine, which has not crashed, will continue executing after your analysis script has crashed, or you can basically guarantee if the analysis script crashes that the simulation engine will at least pause. So it's up to you what happens in that case. The other case where, for example, if your simulation engine crashes, the client will be able to detect that, and it'll continue just with a shorter trajectory, more or less. So if you're expecting more frames but got fewer, your analysis script is going to run on all the frames that you had, and you'll just get intermediate results. But it's not like there's not going to be absolute data loss.
And that's where the option comes in that was discussed a little earlier, like you can specify the buffer size. So basically, if you generate a large buffer, then your simulation continues running. If something happens on your analysis side that it doesn't catch up, then basically you can still accumulate more and more data. That makes it easier also to catch errors like this. So basically, I would recommend in general to give it a generous buffer. We saw examples of 100 megabytes. You can increase that even further to make things more stable. If your analysis script really completely crashes, then once that buffer is at 90%, you basically will communicate to the MD to pause until your analysis catches up. If it's really crashed, it will never catch up, of course, but you will not lose data. So this is not a problem.
I have a question.
Go ahead.
How do I get in touch if I want to work with you guys or collaborate or learn more about streaming or just get involved in general?
So I would basically recommend to join the MDAnalysis Discord channel. So Oliver can probably tell more about that as well as you. That in Discord you basically have a whole community together. There's a special channel for the streaming project. So you can find already a lot of our discussions there, and it's free to join. So just join in and have a look. Otherwise, you can, thanks for the link. And you can, of course, reach us with a myriad of different ways via email and stuff like that as well. But I definitely recommend joining the Discord channel.
Fantastic. Does anyone have any last questions? Final chance, going once. Going twice, sold. All right, we're just going to do a super quick wrap up. And then, oops, sorry. Let me just share my whole desktop. All right. Well, thank you so much for coming today. All of you, it was really a pleasure to get to share the work that we've been doing, and massive thank you to the ASU folks who've done the vast majority of the heavy lifting. It's really exciting what they've built, and I really think that it's gonna have a great impact, scientific impact going forward. So I personally am really excited. I hope you're all very excited too. As mentioned, this is not goodbye. This is just oops, sorry. This is just the beginning. So please get in touch on the MDAnalysis Discord, or maybe if you're a PI and would like to reach out to one of the other PIs, I'm sure you can find their emails. There's also a post. There's also the workshop stuff that's all available at the link specified, and there's also a post-workshop section for you guys to work through that has some information about streaming in general and some useful links. Yeah, but other than that, here are all our socials. Please stay in touch. Especially Discord is a really great way to stay in touch with the MDAnalysis community. And thank you so much again for coming. You're all part of the MDAnalysis community now, so don't be a stranger. All right. With that, we conclude a wonderful workshop. Thank you all. A round of applause to you all. Thanks for coming. It's much appreciated. Bye.
Thanks for joining, everybody.
Thank you so much, all. Thank you again.